So today we'll start the same idea, the same crying and IQ worksheet, but we're going to move into the stuff that's actually new in chapter 14. And so we've drawn the graph and we have the number of cries and the IQ, and we get some equation, and you could graph it or you could look at your calculator and graph it. Well, that's a residual plot. And my first question is, if I added two more children to the mix, what would happen to that line? It does depend on the kids. Um, would the line change? It would probably change a little bit, but it isn't going to change much. Why would it change a little bit? Well, the only way it wouldn't change is if the point happened to be the perfect point that didn't change anything out of kilter. But it probably isn't going to change a lot. I've got 38 kids. I got a good group going here. The new stuff will affect things a little bit, but probably not a ton, but it is different. Now, what if you found 38 kids and somebody else went and found a different 38 kids to test? How would their graph compare to your graph? It'd be a different line, but they'd be real similar, right? So if I sent you guys out and had you do it and you came back with the same line, I'd give you a 0 for cheating. But I should expect you to come back with lines that are pretty comparable, because 38 is a good sample size. I mean, that's a lot of kids. So your lines ought to be kind of similar. You're all coming back and giving me different y hats. So you've got y hat equals a plus bx, and then she comes back and she's got a different y hat equals a plus bx, and some other guy comes back and he's got a different y hat equals a plus bx, but all of these y hats are kind of similar. Now, if the statistical all-knowing God took all the data, you three guys plus all the rest of them, or if we thought of that statistical all-knowing God taking all the possible kids that were or are or could be and did or will be and did the data and came up with the equation, that would be the true regression line. And that true regression line would be the average of all of you guys' regression lines. And instead of saying it was a plus bx, I would come up with some other letters that help me understand that it was the true. And so just like before, I'd use Greek letters, right? So what Greek letter do you think I should use for the y-intercept? I could use omega. Alpha is the one that people besides us have chosen. So we'll go with what they did. So alpha is the estimate for the true y-intercept. And what's the estimate for the true slope? Beta. Now this alpha and beta have no relationship to type 1 and type 2 errors that we did in chapter 10. So don't get confused with that. And this is also why I've encouraged you to use LinReg number 8. Because now that you've used LinReg number 8, what's my estimate for alpha? A. And my estimate for beta is B. And if you use LinReg number 4, then A would be your estimate for beta, and B would be your estimate for alpha, and that would be really confusing. So we like to use the 8th LinReg, A plus BX, so that it looks like this, so that A is the estimate for alpha, and B is the estimate for beta. Now, what we're going to do in chapter 14 is hypothesis test with this. And the way that your hypothesis test looks is like this. HO, beta is 0. And in this particular problem, HA is beta is greater than 0. Now, what does beta represent again? The true slope. So if the true slope is 0, what does the line look like? Horizontal. Great. Second period said it's straight. It's like, yes, it's a line. It's straight. But it's horizontal. That's what I'm looking for. So if the true relationship is horizontal, how does my guess for y change as x changes? It doesn't. It doesn't. So if this was my x, then I would guess this y. But if this was my x, I'd guess the same y. Because what it means if beta is 0 is that there is no linear relationship between x and y. And in this case, x and y is crying in IQ. And in this problem I'm doing here, I'm doing the one-sided alternative. Beta is greater than 0. There is a positive linear relationship between x and y. So I know that the slope of the problem that I had us work on part 1 gave me a slope of 1.49. It appears to be positive. But it was also 1.49, and it was from you guys, 38 kids. Well, not your 38 kids, but the 38 you sampled. Please no, right? If we did a different 38 kids, would the line still be positive? Or is the true line believed to be positive? That's what's going on with the HO and HA. Now, there's a bunch of stuff on your worksheet that you can go through. I'm going to try to explain it all to you so it makes sense, and then you can use the worksheet as a reference. Let's flash back to chapter 10. In chapter 10, we had a z-test statistic, x bar minus mu over sigma divided by the square root of n. If I read that in generic terms, I would say the test statistic equals, what did I call this? The estimate minus the true or the parameter divided by standard deviation, right? So now let's convert that same idea, the test statistic equals the estimate minus the parameter over the standard deviation, to what we'll do in this chapter. Now, if what we're doing in this chapter is beta is 0 versus beta is greater than 0, my test statistic, I'll explain more in a minute, is t. We're back to the t distribution, or the green chart. What is the parameter going to be for this test? Beta. So what's the estimate? B. And the standard error is the standard error. Now, I haven't given you the formula for standard error yet. I'll explain that. But it's the same concept as what we've done before. The estimate minus the parameter over some standard error. For the sake of what we're arguing here, what is beta supposedly equal to? 0. So sometimes this is written like this. And when it's written like this, it's called the t ratio. I personally like this way better because I think it follows more in line with what we've done in the other chapters. But beta is 0, so it's essentially the same as this. Okay? This stuff here is not on your formula chart. The formula for the standard error of beta, or standard error of B, is on the formula chart, and I haven't given that to you yet. But the reason this isn't on the formula chart is because it's the same thing. I mean, I guess it is written there generically. Test statistic equals estimate minus parameter over standard error, but it's not written like that. So now we got to talk about the standard error. First, let me say that the degrees of freedom for this chapter are n minus 2. Now, the way I remember it, it's because you've got two variables, an x and a y. Each one subtracts 1, and we end up with n minus 2. That's not really the whole story, but it's good enough. The two variable problems, we've got n minus 2. Now, a few of you are thinking, wait a minute, we've done two variable problems before. We have not done two variable problems before. We've done two sample problems before, and that's a very different deal. If I find the average height of you guys and the average height of my third period class, that's the same variable on two different groups of people. Now I'm looking at two different variables, such as the crying and the IQ. Two different things on the same group of people. When I do that, I'm turning it into a two-dimensional graph, like a scatter plot. And that's what's going on back in chapter 14. So here's the degrees of freedom. The formula for the standard error of B is, it gets a little bit complex, or complex looking, but it's not really all that bad. The standard error of B is S over the square root of the sum of x minus x bar squared. Now, of course, you're like, do we have to know how to do this? Yes, you do have to know how to do this. First period, they asked me, can you show us the simple way to do this on your calculator? Yes, and I will. But simple just means straightforward and easy. It doesn't mean short. Okay, it is simple to do on your calculator, but there's a lot of steps to it. This SEB means the standard error of the slope. Now this is S, obviously, this thing on top, and I got to give you the formula for S as well. So S is the square root of 1 over n minus 2 times the sum of the residuals squared. S stands for standard deviation. Now, we've talked about S of x before. That's the standard deviation of x. It tells me how far all the x's are from the mean. The standard deviation of y tells me how far all the y's are from the mean of y. This is a different S. I know they're all over the place. It's unbelievable. But this is a different S, and it's basically telling me how far the points are from the line. This is a two-dimensional standard deviation. So here's my calculator. Let's go back and look at the residual plot. So I'm going to look at this one more time. All right, here's a residual plot, and these distances are called residuals. If I sort of look at the average residual and how spread out that average residual is, that's what this S is all about. So let's go through and calculate this stuff, this t-test statistic with the calculator and see if we can figure it all out. So if I'm going to calculate the t-test statistic, B, of course, is easy. B for this problem was 1.49. But I got to figure out the standard error of B. And in order to figure out the standard error of B, I have to figure out this S, the standard deviation of the line. So this is the part I'm going to start with. And I'm going to take it one step at a time. You can go a little more expediently than I'm going to go, but I'm trying to walk you through how to do this to show you it's not that hard. There's just a bunch of steps to it. So if you have not done so already, you need to do linear regression. You can choose to store it into Y1 if you want, or you need not. It doesn't matter to me, but do regression. In the process of doing regression, you're also making residuals. You're also calculating X bar and Y bar and S of X and S of Y and all that other stuff. It does 2-var stats in the process of it. So by doing this, we calculated residuals. So go to your lists, and in L3, we're going to copy the residuals. To copy the residuals, it's second list, resid. What is the sum of L3? 0. That's why we have to square it, because otherwise we just get 0 when we add it up, and what's the average of 0? 0. Doesn't matter. So let's square L3. L3 squared. Now what? So look at my formula. Now what? Now add them up. So for my home screen, I'm going to sum up L4. It's second list, math, number 5. Now what? So now we're gonna multiply that by 1 over n minus 2. There were 38 kiddos, so 38 minus 2 is 36. Multiply this by 1 over 36, which is the same thing as dividing by 36. And then I've got to square root that number right there to get S. So S for this problem is 17.498. So now to find the standard error of B, it's that 17.498. So I know I'm going to need that number again. I'm going to store it into the letter S. I could have stored it into whatever letter I want, but S seemed reasonable. So I'm going to store it into S so I can come back and get all those digits out of it in just a second. So now I need to figure out this bottom part of the SEB formula. Okay, so to do the bottom of this right here, I'm going to go back into my lists, and I don't really need L3 and L4 anymore, so I can delete those dudes just so they're not bothering me. And now's probably a good time to remind you that if you actually delete a list, it disappears, the list is gone. So you have to insert, it'll give you a blank list, and you can rename it whatever list you deleted, because deleting does not clear it. So for example, if I delete L2, my L2 went away, but as soon as I insert and name that inserted list L2, there's L2, because deleting is not clearing. So clear if you want to clear it. Now in L3, I'm going to do this stuff down here on the bottom, x minus x bar squared. Where are my x's? L1. L1 minus, now I got to do x bar. Now your x bar is a refresher. If I press vars, statistics, number 2, I get an x bar. Then I get this stuff. Now I need to go back to my home screen and add up L3, and then I'll square root that. So I'm going to add up L3, and then I'm going to square root that. So that number is what goes down here on the bottom of this fraction. So 35.932. And then the easiest way for me to do that is to remember that I stored this in S. So I'm going to go alpha S divided by that answer to get that number, which is my standard error of B. So now that I figured out the standard error of B, I can go back into this and find the actual t-test statistic. So I'm going to get rid of some stuff so I've got some more room. I'll tell you what, maybe I can move this over here. And so my t-test statistic is B over SEB. From memory, I know this was 1.49 and SEB is 0.487. But watch this little trick because this is pretty good. There's the 0.487. So I need to go B divided by this number. Here's how to get to B. VARs, statistics, EQ for equation, letter B. B divided by answer. There's my t-test statistic. It's 3.065. Now my graph, it's a t-distribution with 36 degrees of freedom. Here's my test statistic. There's my p-value. And if I were using my calculator, which I'm going to do, it's TCDF of a lower bound, upper bound, degree of freedom. So on my calculator, I go second distributions, TCDF, lower bound, upper bound, degree of freedom. That number right there is called my p-value. So my p-value here is 0.002, which is pretty small. So what do? I reject HO in favor of HA. I decide that I no longer believe that there's no linear relationship, but I now believe there's a positive linear relationship between crying and IQ. I haven't gone through all the conditions and all that. I'll do that with you on Monday, but I want to show you one last thing before the end of the class here. Stat, test, Lenreg t-test. Coach, do we still have to do all this stuff? Yes. You have to know how to do all this stuff. But check it out on the calculator. Your X lists are in L1, Y lists are in L2. What is this little symbol again? Rho. Good. That's the true R. What's R? Correlation. So the true correlation and the true slope have the same sign. If the slope's positive, the correlation's positive. So that's what we're doing, the one-sided test here. This sentence right here, it's asking you if you want it to save the Y hat line. Yes, you do want it to save it. Where do you want it to save it? Save it for me in Y1. So when you do this function, it's actually doing linreg, it's doing 2var stats, it's doing all of that at the same time. So it's doing your residuals, so it'll save it for you. Calculate, chicka chicka whir whir, gives you all sorts of useful stuff. T-test statistic, p-value, degrees of freedom, your y-intercept, your estimate of the slope, your S, which is your estimate of sigma, the true standard deviation of the line. It does not give you SEB. It did not give us this 0.487, but it gave me R and R squared, and it'll do that even if your diagnostics are off. And so certainly you can use this Lenreg t-test function on your calculator. So now we want to look at a confidence interval and kind of do the same idea. So for a confidence interval, you remember, for example, back in chapter 10, it was x bar plus or minus z star times the standard error. Same format here, but now the estimate is b. The critical value is a t star, and the standard deviation is the standard error of b. So we remember the b is 1.49. I'll come back to t star. Standard error of b is 0.487. If you were using your yellow calculator or some TI-84 calculators, there's a function on there that'll do this t star for you. Let's say we wanted to come up with a 90% confidence interval. Those two areas are 0.05, t-distribution 36 degrees of freedom. Under distribution, there's an inverse t function, and the arguments would be 0.0536. Now you could also use your chart to do it. Your chart might not have this row of degree of freedom, so if it didn't, you would have to slide up the row until you got to 30 degrees of freedom. But if you have this function, you see the t star is negative 1.688. We actually use the positive 1.688. And then I'll use my calculator to go 1.688 times 0.487. So I got 1.49 plus or minus 0.822. 1.49 plus 0.822. 1.49 minus 0.822. So I'm 90% sure the true answer is in there. Or I'm 90% sure that the true slope is in here. Or I'm 90% sure that the true slope of the regression line between CRIs and IQ is in here. Now, all that's good. I personally like to say it something more like this, though. I'm 90% sure that for each additional CRI, we can expect to see an average increase in IQ of somewhere between 0.67 and 2.31 points. I like that sentence, probably the best. And just like with the inverse t function, if you're using an 84 calculator, there's a function under stat test down here that says linreg t int, and this will do a t interval just like we've got here. But of course, you need to understand the concept of the formula and how all those numbers plug in as well. That's part 2 of the worksheet. We'll talk about the conditions and sort of wrap it all up in part 3.